So if I compare the first ionization energy going to a +1 to the second ionization energy going to a +2, the second ionization energy will always be greater than the first. Because instead of pulling an electron away from a neutral atom, I'm pulling it away from a positive atom. Okay, so here, I think this is magnesium. The first ionization energy is about 0.9. The second is almost twice that, 1.8. So it still wants to get rid of both of them, but that second electron is just a little bit harder to get away. Okay, and that's true for every element. All right, if we think about what's going on with the orbitals, there's a reason why that takes place. Okay, so for oxygen, the first ionization energy we said was this. Okay, but when we take away that electron that's paired and go to oxygen plus, okay, all those orbitals are sinking down in energy. They're more attracted to the nucleus because the nucleus still has a +8 charge, but there's only 7 electrons. It's pulled in tighter. So if mom has one of its electrons kidnapped, she's going to hang on to the other ones. Maybe it used to let the kids play out in the front yard. Now she's going to be like, nope, I'm going to have my eyes on you at all time. Okay. So once that first one's gone, it's harder to take away the second one. Okay. And the trend continues. The third one's harder than the second. The fourth one's harder than the third. Okay. So that's why that happens. That's our second ionization energy. All right, the other thing this graph is showing is that we have this trend where we have little bit more and then a really big one. So why is that going? Why is this third one huge? Valence electrons are easier to pull out. 4 electrons are hard. So we can count how many valence electrons something has. So sodium has 1, magnesium has 2. So we said this was magnesium. For the third ionization energy, valence was 2, valence plus 1 is 3. So for valence plus 1, that's going to be very large. It's very hard to pull something out of the core. Okay. Now, if I look at sodium, sodium only has 1 valence electron. So for sodium, this would look like a small first one and then the second one huge. If I were to look at carbon, it would be small, a little bit bigger, a little bit bigger, a little bit bigger, and then the fifth one would be huge. Okay, so the way you have to figure out which one's going to be huge is you figure out how many valence electrons there are and then add 1. All right, now if we look at aluminum, how many valence electrons does aluminum have? Show me with your fingers. What do you think? How many valence electrons does aluminum have? 3, right? 1p and 2s. So even though the s are a little bit lower, they're still part of that valence. So which ionization energy is going to be really huge? 4. Okay, now if I'm looking at calcium, okay, fine, calcium has 2 valence electrons. Which ionization energy is going to be huge? 3. Okay, those are really the key things you need to know about those. I'm just going to like zip through electron affinity. So we're not going to worry about electron affinity. The trend's basically the same. There's lots of exceptions, blah, blah, blah. We did talk about electronegativity. This is on your chart that I printed out. And then after I printed it, I realized you can't really see these. You'll understand why in a minute, but we're not really going to worry about what the numbers are. We're just going to use the rule of thumb that the closer it is to fluorine, the more electronegative it is. So I might do boron versus oxygen. So between boron and oxygen, which one's closer to fluorine? Oxygen. So oxygen is more electronegative. I might do sulfur versus tellurium. Between those two, which one's closer to chlorine? Sulfur. So sulfur is more electronegative. Now, what if I go on the diagonal and I compare oxygen and chlorine? The one that is closer to the top will be more electronegative. So oxygen is more electronegative than chlorine, nitrogen is more electronegative than sulfur. I'll try to avoid that, but then that's the general rule if that does. Notice that this upper corner where all of our nonmetals are, we have pretty high electronegativities. Most of our nonmetals are 2 or above, and the ones that are right at 2 tend to be our semi-metals. Okay. are things that are really metallic down here that had high metallicity, francium, cesium, barium, they're less than 1. They have very low electronegativities. So we're really going to be looking at, is it a metal or is it a non-metal? And use that as our basis of comparison. Now you will see there is, this group is called the platinum group here. There are some exceptions to some pretty high electronegativities in there. Notice those elements, platinum, gold, palladium, those are our precious metals. The high electronegativity means that they are less likely to rust or corrode, which is one of the things that makes them so precious. But for our purposes, we're not worried about those. So we're just going to ignore those and just use this general trend, just like with atomic radius, we're going to pretend there are no exceptions, that it's just as we get to fluorine, that's the most electronegative. Okay, we said last week that it describes the tendency of an atom to draw electrons to itself in a bond. And that's why we leave off the noble gases, especially in general chemistry, because there's not a lot of bonding. In reality, yes, noble gases can bond, and yes, they are more electronegative than the halogen. This one is called types of bonding, and this is in the chapter 7. So if you want to look for it on Canvas, that's where it is. Okay. So we have 3 types of bonding that we're going to be looking at. So this is where you might want to pull out this sheet and take some notes on here. I'm going to be talking about metallic, ionic, and covalent. And I'm going to go like back and forth and in between here. I'm not going to go straight across. We will talk the least about metallic because we're not going to do a lot of metal chemistry in this class. But we do want to talk about the type of bonding. So metallic bonding, the way we recognize it is it's between 2 metals. Okay, so I said we're not going to worry so much about the electronegativity. We're just going to say, are they metals? So now we have to go back to what we talked about last week. How do we know it's a metal? We're going to look on the periodic table here, and we're going to say if it is to the, yes.
I didn't get large.
So if it is to the left of that, our transition metals, our rare earth metals, our alkali metals, all of these are metals. They can participate in this. Now, normally we talk about them just as like the pure element. So it's just gold, or it might be an alloy. An alloy is a mixture of 2. So brass is copper and zinc. Okay, so if I have the only thing that's part of what I'm looking at is a metal, this is the type of bond. What we say is the bonding is a sea of electrons. Okay, so the sea analogy is based on the idea that the electrons, because the atoms are so big, remember our metals are big, the electrons kind of wander all over the place. So remember I talked about lithium, the electron could wander all over the neighborhood, right? Well, if we have a whole neighborhood full of atoms like this, all the kids running around the neighborhood, when it gets dark, the kids have to be in bed. But the parents don't care which kid is in bed as long as a kid is in that bed, okay? So the electron that was there today might not be there tomorrow. And this is how we get conductivity. The electrons can move from atom to atom with very little energy, okay? And so that allows for electrical currents. All right, so on your paper, you have, what holds the bond together, that's where you should write sea of electron. That's a fairly common terms. The type of atoms in the bond are only metals. And then a particle view is going to look something like this. So the red positives there, that's the core. That's the nucleus, and all the core electrons are there, right? And the blue dots are the valence electrons, mostly the s electrons, but the valence electrons that can kind of go from place to place. Okay. So the core is forming a pretty regular pattern here. These form crystals. Okay. The electrons, they're random. They can kind of go anywhere. Okay, so very loosely held. All right, now to further this water analogy, imagine that you are at a lake or at a swimming pool with other people and you're swimming around. You don't ever say to somebody, I'm sorry, that's my water. You can't swim with those. You can't play with those water molecules. They're my one, right? We all share all of the water molecules. And when I move over here, some of those water molecules are going to move to you, and I might pick some up from somebody else. That's kind of how it is with these electrons. They're all just willy-nilly moving in. So sea of electrons. All right. When we have an ionic, well, actually, let me stick to the box. Covalent is when we have only non-metals. Okay, so this happens when we have just the metals. When I have only non-metals, then I have covalent bond, and that's where they share the electrons. Okay, so why do two atoms stay next to each other? Because they're sharing the electrons. Marriage stayed together for the sake of the kids, right? Hanging on, they're both hanging on to those kids. So the second thing that says types of atoms, that's going to be only nonmetals. And we'll get to a particle view in just a minute. Okay, ionic then is when I have some of each. Now it might be 1 and 1. I might have one metal and two nonmetals. I might have polyatomic ions, but I'm going to have both. Okay. The reason they stay together is because opposites attract. The positive cation, remember the word cation, you're going to need to know that, and the negative anion are attracted to one another. I'm going to illustrate this because A, it's in your book, and B, if you take PChem, you'll see this again. I'm not going to test you over this, but this is one way to conceptually think about covalent bonds. Like I said, we're jumping around a little bit. This is covalent bond. So if we start with two atoms that are separate from one another, and they each have their own electrons, they're not really sharing, that's not really particularly stable, okay? The lower this line goes, the more stable it is, right? So we're right out here. That's not particularly stable. This is where they're so far apart they can't even tell each other's name. The 0 dash line. Okay? But they've just started to see each other across the dance floor. When they get closer together and the electrons can start to move between each other, then we've got a little bit more stability. It's lower in energy. So lower down on these diagrams means more stable. That's a good thing. The universe likes that. When they've gotten so close that they can share all the time and they're not really separated, we're down here. We call this the potential well. So think of like a well where you might get water. It's a hole. Okay, this is the well. So it goes way down in energy. But then it starts to go up again. If we keep pushing those two atoms together, not only are the electrons going to get closer together, but the nuclei are going to get closer together. So if we push too hard, we're going to try and get those nuclei on top of each other. And they're both positive. They will push away. And so that's what this side is about. So the nuclei is pulling each other away. So there's this perfect distance for those two atoms to be, where they're close enough that they can share, but they're not feeling smothered. Okay. And that's what we call the bond distance. On a graph like this, this would be the distance from here to here at the bottom of the well. That's going to be the bond distance. And what usually happens is that rather than sitting at the bottom of the well, the bond goes back and forth just above the line. It gets a little closer, it gets farther. Called a vibration. We'll get into vibrations later. Okay. So remember how to find your metals. You know where that diagonal line is. Know which ones are metals, which ones are not metals. All right. Know which things form cations. Know which things form anions. We looked at this graph the other day, where remember our anions get a little bit bigger. So the red is the neutral atom, And the gray is then getting a little bit bigger when we add the electrons. And it grows a bunch when it adds the first electron. After that, it doesn't grow too much. But the bigger change is going to form a cation. So on the blue side, blue is neutral and gray is the cation, and those get a lot smaller because we're generally going down to the core for that. Now this box here, if we were to count the number of electrons in that box for each of those atoms, it would be the same. So fluorine has 9 electrons and I make it 1 negative. I added 1 more, so I have 10, right? If I go to nitrogen, it starts out with 7 electrons and I add 3 more because it's 3 negative, I have 10. Okay, same thing with magnesium. I start off with 12 to make it plus 2. I take away 2 of those, I now have 10. So when all of these atoms have the same number of electrons, we say it is isoelectronic. And that's a term you should know. Isoelectronic means they have the same number of electrons and their electron configuration would be the same. So they all have the same electron configuration as neon. Isoelectronic means it has the same number of electrons. So iso means the same. All right. So I like to draw this triangle to compare our different kinds of electrons or different kinds of bonding rather. So if I have a difference in electronegativity going up, and then I have how electronegative it is going from side to side. On this side, sodium is low electronegativity, and on this side, fluorine is very high electronegativity. So if my 2 atoms are both over here, high electronegativity, I call that covalent bonding. And if they're both over here, low electronegativity, I call it metallic bonding. But if there is a difference in electronegativity, then I might have it be ionic. So ionic means I have a really big difference. So 4 for fluorine and 1 for lithium, right? That's a really big difference in electronegativity, 3. Okay. So down here I have no difference, and up here I have a lot of difference. There's a lot of shades in between. Okay, and so we might think to ourselves, well, how do I know when it is actually covalent versus ionic? And how do I know when it's non-polar, which means there's no difference, or when it is polar, which means there is some difference? Okay, so metals are loosely attracted, low electronegativity. Oops, non-metals are high, strongly held electrons. I'm going to skip over that for a second. Okay. Nope. Gotta go back. Okay. So from your book, I thought I had this on here, but I don't. If the difference in electronegativity is greater than 1.8, we would call that ionic. So like I said, between lithium and fluorine, we would say that's 3, and that's ionic. But I don't want to memorize the periodic table and all of the electronegativities. So what I'm basically going to do is I'm going to say if I have a metal bonded to a non-metal, that's going to give me an electronegativity that's probably 2 or greater. There's going to be some exceptions, but for the most part, we're just going to say that's going to be ionic. Now, I also have the condition where I have the electronegativities are closer. So maybe it's 1.5 or 1.1, but it's not really very close to 0. And we're going to call those polar. All right. And I'm going to have to go back here. So if I have a really big difference, we say it's ionic, there's no sharing. If they're the same, we say they are sharing with one another and it's purely covalent. If there's a difference, but it's small, we say they're polar, and we use this arrow. So it's an arrow with a little plus sign on the positive side. Okay. Most bonds are going to fall somewhere between purely ionic and purely covalent. Okay. So we talk about, does it have ionic character? Does it have covalent character? And a lot of bonds are going to have both. So that's where you're going to look at, well, what are the elements? If it has both characters, if one's a metal and one's a non-metal, we're going to call it ionic. If it has both, but they're both non-metals, then we're going to call it covalent, polar covalent. All right, so this graph is looking at what percent is covalent, what percent is ionic. And if I'm halfway in the middle, it's calling that our dividing line. And if we look at the difference in electronegativity, which is this here, that's a pretty good indicator, like right about 1.8. That's where we see all of these over here, but there are exceptions. So HF, hydrogen fluoride, even though it has a difference in electronegativity of 1.9, very high, it actually has some covalent character. And as we get into acids and bases, that covalent character becomes important. That's why it is not a strong acid. It won't completely separate that hydrogen when it's in water. It stays firmly attached because of the covalency. In contrast, lithium iodide acts more like it is ionic, so it has more ionic character, even though the difference in electronegativity is small. Okay, so that's why we have that difference. I'm not going to make you do anything with these graphs. I just want to illustrate with this how much sharing is going on. So lithium and fluorine, this well here between the two of them is all the way down to the ground. That's showing no sharing going on at all here. If I compare other combinations to hydrogen, this dip is nowhere near the bottom, right? This is all that sharing that's going on between the hydrogen and hydrogen. This is all that sharing that's going on between the two fluorines. So that's covalency, sharing. Here, they're doing a lot of sharing. That dip isn't anywhere near the bottom. But most of this is green, telling us that the fluorine gets to hang on to the electron. And since it's hanging on to the electron, it is, it's the more electronegative side. And this is where we see this arrow, this dipole arrow, with the plus on one side. The plus shows us the positive side, the arrow shows us where the electrons are going. I will not give you those diagrams on a quiz or a test, just to illustrate, it's just to illustrate sharing, okay? So these are some cartoons. If I compare hydrogen to oxygen, even though hydrogen is very small, usually the smaller ones get to hold on to the electrons more. Oxygen is more electronegative, sitting over by fluorine. Okay, so that's very electronegative. Once I have a polar bond, I often, not always, but usually will create a polar molecule. So these guys are ice fishing, hydrogen, hydrogen, oxygen, because this is a polar molecule. All right, I think I'm done. Yes. Okay, so now we are going to go back to your handout there and look at some of the other things that we might want to know about the differences between different kinds. So we mostly looked at the top part. Thinking about particle views, we already drew a particle view for metallic. If I'm going to show a particle view for ionic, these do not form molecules. So it's not really fair for me to say, okay, I have a positive and a negative. This guy's little because he's a cation. This guy's big because he's an anion. That's not really fair because that looks like a molecule. Really what's going on is I have positive, negative, positive, negative. Each positive is surrounded by negatives, each negatives is surrounded by positives. The particle beam might look something like this for an ion. Okay, now if I had a +2 and a -1, there'd be twice as many of the negatives. But no molecules, right? It just goes on and on and on for billions and trillions and quadrillions of atoms. When I have a molecule, I have them sharing. So I can show this a couple of different ways. Let me do this. Sometimes we show overlapping circles to show them sharing, and then we might have two little dots in there, which you guys can't see, but you might have that. But what is more common is for us to use the element symbols and a line in between them. Okay, maybe I have this. Okay, so each of these lines is 2 electrons. We're going to have to remember that shared electrons come in pairs. With the metal, it's just everyone for himself all over the place. But when we're sharing the electrons, it's 2 at a time. When I do the formula for molecular compound, it's just the number of atoms that are in it. H2 or CH4, right? But when I'm doing ionic or metallic, I can't count all of the atoms because there are no molecules. So for metal, I just put whatever element it is I'm doing. AU. That's gold. If I'm doing ionic, I do the empirical formula. Remember, empirical is the lowest ratio. So up above, I have a 1+ and a 1-. That might be sodium chloride, right? I might also have a polyatomic ion, right? So this is my cation, the magnesium, the positive. This is my anion. And what's the name of the anion that is SO4 2-? Sulfate. Okay, so when I name these compounds, I just name things in order. And if it is a polyatomic ion, I'll just use that name, so magnesium sulfate. If it is just an element, then I change the ending to I. So I don't say sodium chlorine, I say sodium chloride, right? Okay. One other thing that we can have over here is we can have network covalence compounds. In a network covalent compound, we have sharing between 2 atoms. But what ends up happening is I have something like carbon. It doesn't have to be carbon, but often things with carbon in them that can form many bonds. So carbon can form 4. And so it's got arms reaching out in all directions. And so when it grabs onto the next carbon, that one's reaching out in all directions. And then the next one's reaching out in all directions. And so instead of forming like a nice line or a ring, sometimes it can go on and on and on in a crystal structure. And we get things like diamond or quartz. So diamond is just carbon and quartz is just silicon dioxide. So again, we go back to the lowest ratio. All right, we will look at the properties of the solids on Wednesday, and then we'll get into section 7.3. So take a look at 7.3 before Wednesday. And have a good week.